All right. Hey, folks. Thanks for showing up for the image processing tutorial. So today we're going to be talking about geologic image processing. And really, I want this to be a bit more of a cookbook and kind of something you can use in your own time. So first off, if you're just joining us and you didn't get the note that I didn't send about the location of things, this is in GitHub, and I'll add the link to the YouTube comments in a bit too. But this is in GitHub. If you're on Swung, Software Underground Slack channel, join the T20 Thursday images channel, and there's a link to all this material there. So this is a Jupyter notebook and a repository of kind of data and the like. And just to mention that in case you are looking for it and can't find it, it is be a little hard to copy a link, but I'll point it out. Geo image processing tutorial. If you search for that, you should be able to find it on GitHub. So I just want to kind of mention that just in case folks haven't found it. Also want to point out if you're just getting set up and you don't want to have a full local Python install or you're having trouble with it, there is an option for Binder. So if you go to the GitHub page, you can launch that. That will let you run all of this in your browser. It's limited in the number of people that can run it simultaneously. So if you are comfortable running locally and you don't mind doing that, I'd appreciate if people would. But if for any reason it's difficult, feel free to use Binder. Also, if you just want to watch, that's perfectly okay too. This is going to have interactive components, but it's also something that you could watch and gain a lot from just watching and talking about it. And you're welcome to walk through this in your own time later. So don't feel the need to spend every minute here. But let me say a bit about what we're going to do today. The real thing here is images are more than just a photograph. I think we're all used to photograph, satellite imagery. That makes sense. But image processing often is anything it's really anything that's regularly sampled. So a lot of data sets in geology, you can use image processing methods on that you might not otherwise think of. Even 1D data sets like time series, often there are image processing methods that wind up being useful, the same filtering methods. So what I'm going to talk about today, a lot of it will extend to any number of dimensions: one-dimensional, two-dimensional, three-dimensional, so things like seismic volumes; four-dimensional, things where you may have a volume moving through time. It's really common with weather data. Some of it will just be two-dimensional. All the examples I'm going to show are going to be two-dimensional, but I do want to mention that a lot of these methods are useful elsewhere. And so today we're going to go over several specific exercises. We're going to start out spending a lot of time working with some bathymetry data. And that's mostly just because it's a very familiar data set type for most people. Um, I don't have to explain what elevation data is. Everyone can kind of intuitively understand it. And so we're going to spend a lot of time talking about that and walking through different methods. But we're going to do an exercises on those that are going to focus on things you might actually want to do. So in this case, we're going to try to detect some seamounts automatically, try to get the boundaries of those seamounts. We're going to display it with different types of hill shading and talk about slope calculations. We'll also try to calculate the toe of slope, figure out exactly kind of where the edge of the seamount is. And then we'll do some more fun stuff, and this will move a little faster towards the end, but we're going to do some lineament analysis from aerial photography, so try to look at fractures and things along those lines. We're also going to try to do some grain detection from thin sections and look at overall kind of shape preferred orientation in thin sections, and try to do it in a crude way without having to measure too many different grains. So it's not going to be perfect, but it'll at least give you some idea of kind of a common workflow there. Um, One thing to point out is that I'm not trying to replace desktop tools you may be familiar with. So ArcGIS, ImageJ, Photoshop, you may have used a lot of these things in geologic workflows. This is not meant to replace these at all. This is meant to, oh yes, good point. So let's just go ahead and get this a little larger because it'll be easier on everyone, I think. And I may make that a little smaller if I need to, but thanks for pointing that out. The size of the text is also a key thing. I'm also going to go ahead and hide this really quick, if that's all right. And we'll just get rid of that too. That'll be good enough for the moment. Okay, so hopefully we can see a bit more now and everyone can read it. Anyway, back to the goals. I'm not trying to replace the desktop software necessarily, but I do want you to be able to understand how to use Python libraries and chain them together because they're lower level operations. In the desktop software you may have used, you often learn building blocks that are much higher level than what the image processing libraries expose. So the real purpose of this is if you're familiar with some of these tools, to understand how to use the kind of lower level blocks like Indie-image, scikit-learn. There's a lot of these. Understand how to string those together to similar workflows so that you can do some of the things you might otherwise do manually automatically. And it's often you want to adjust parameters visually, and so it doesn't make a ton of sense to code it up. That's fine. Other times you need to run it on 1,000 things, and you want it to all be the same settings, and that's really where this can shine. Um, what I'm not going to go over is a ton of the Python specifics and a ton of NumPy specifics. So if I use some indexing tricks you haven't seen, I'm happy to explain them, but I'm going to gloss over them a bit. There's a ton of great tutorials out there for that, and I'm actually going to link to some of those. So definitely read up on those too. Um, I'm also not going to show a lot of common libraries like OpenCV. We're going to stick to just really two libraries, which is scipy.indieimage and scikit-learn. Sorry, I put scikit-learn. That is supposed to be scikit-image. Um, well, there we go. First typo of the day, folks. That should say SK-image. Anyway, that's essentially what we're going to focus on today. We're also going to use Rasterio a bit. That's a library for reading in and writing geospatial data. And I will show a little bit with vector data too. So this is going to show some of the geospatial stuff, just because one of the things you want to do is be able to get data in and out. One thing I do want to mention, I will try to kind of keep abreast of questions a bit, but there's a significant lag between me presenting this and what you're seeing on YouTube. So it may be difficult for me to answer questions. So I'll probably try to answer questions mostly in the breaks. And I do apologize for that. It's just a matter of this is going to be a little less hands-on than an in-person tutorial would be. But hopefully you can still feel free to ask questions and still free to walk through things. And really feel free to come back to this later and walk this on your own. I'm really hoping this can be something that's not just this presentation and something you can play around with. Okay, so additional resources. One of the things I mentioned were these other tutorials. I really have to mention SciPy Lectures if you haven't seen it before, even if you're familiar with the Scientific Python ecosystem. SciPy Lectures is great. I believe it was Nicholas Roget, but no, it wasn't. It was anyway. It's one of the very big names in scientific Python who put it together, and really it's a fantastic resource. So I would recommend looking through it, even if you're familiar with everything. It's just a good guide, and it covers some of this in simple ways. We're going to go in a little more detail on the image processing side, but it's really a great resource. And there are also tons of tutorials for libraries we're going to go over in detail. They're much more detailed than what we do here. I'm going to focus on specific applications in geology, but feel free to read these tutorials. They're they're wonderful resources, and they're a very good thing. Okay, so I've talked quite a bit here. One thing I do want to go ahead and dive into, though, is our first exercise. I'm going to try to structure this around concrete tasks, and we'll talk about methods, but we'll talk about methods in the context of solving a specific problem. And let's start out with a problem that I think will be fairly intuitive. We have bathymetry of the ocean, and so this is oceanic crust. For those of you who aren't geologists, it means it's going to be fairly flat, and then the seamounts intrude later, and they're going to rise up very quickly from it. So they're an interesting thing to identify, and they're pretty obvious. So to give you some idea of this, I will mention there's an example that has this full worked example we're going to do. I'm going to show it, but we won't actually run it here. Just to give you some idea, if you want to look at that on your own, feel free to. We're going to walk through this in steps. This is kind of a big wall of code, and there's a lot there. So we'll just take that back out, and we'll come back to it later. All right, so let's go ahead and talk about our bathymetry. First thing we want to do is look at it. Well, all right, we back up just a second here. What are we actually dealing with? We've got a 2D array, and that's how images are represented. So we've got kind of this data. It's regularly spaced, regularly sampled, and in this case, it's integers. I do want to point that out. So one of the things we're going to do here is look at this. Notice we do actually have integer values. They're all negative. This is bathymetry. It's almost all subsurface, or sorry, submarine. So the negative indicates, below sea level. Just want to point that out because it's always good to step and take a look at your data before you immediately start visualizing it. Not a whole lot to say here. This is GEBCO data, it'd be the Western Pacific. Now let's actually take a look at it. Okay, so what we've got here is a plot, and you can see a color bar. We have some positive values, a lot of negative values. White values are high, dark values are low. And, you know, if we hover over, we can actually, oh, well, I guess it's a little too big. There we go. You can actually see some of the values as we hover. One of the things that we're going to look at here, though, is just displaying this in different ways. So it's not that great to look at it from a simple grayscale plot. It'd be nice to apply a color bar to it. So we've applied a color bar already. I know people think of grayscale as not a color bar, but it is. So let's go ahead and show it with a nicer, more kind of color bar that we're used to seeing. Tell you what, these figures are a little narrow. I didn't think about my browser size. If it's okay with folks, I'm going to increase this a bit, just enough that we can see the full plot in each case. It'll save me a little bit of trouble later finding things. So hopefully everyone can still see okay. If you're going along on the phone, this might be a little bit difficult, but I think for most of the aspect ratio of YouTube streaming, I think we're probably okay. So I just made this a little wider. Anyway, back to the topic. All right, blue colors. This looks more natural. It's what people are used to seeing. I just want to point out that we are still dealing with a single band of integer values. We're displaying this as RGB for the rendering, but we're still dealing with raw, raw numbers at the end of the day. All right, just to point out what we're seeing here. We have this kind of background of the abyssal plain. It's oceanic crust, about 4 kilometers depth. That's going to be important later. And we have these seamounts rising up above it. There's a lot of them. And we might want to automatically get all of the outlines of those. We could do it by hand, but it'd take a while just to digitize all the outlines. Pretty obvious. So let's try to basically go through and just automatically detect them. It should be something that seems pretty reasonable. We could look at, just the elevation. We can look at potentially a few other things. This seems like a tractable problem, but it's a good place to start. What it lets us talk about is concepts like thresholding and concepts like filtering. And these are really key to a lot of image processing work. And also, this will be a type of segmentation. So I'm going to talk about those terms more here in a second. But just remember thresholds, filters, segmentation. Let me say a little bit more about segmentation. Segmentation is any way that we're trying to split up an image. We're trying to say this part is distinct from that part. And thresholding is one way of segmentation. It's kind of the simplest way. So with that in mind, let's think about the simplest way we can detect these. We have elevations. The seamounts rise up above some fairly constant background value. We could just say a seamount is anything that's over some value. And that's a threshold. So it's no real surprise. I think everyone's probably fairly familiar with it, but I just want to work through kind of how this works. So in NumPy terms, we have this array of values. Bathy, we're going to say it's greater than 3,500. 3,500 in this case is 500 meters above kind of the average background oceanic crust depth. So there's actually some reason for that number. But let's look at what we get when we do this. For those of you who may be familiar with NumPy, this is no surprise. It's a bunch of true and false values. There are trues in there. We're just seeing the edges of the array where there don't happen to be any. We usually want to work with numbers in image processing. So true false values underneath the hood are stored as zeros and ones. And so a lot of times we'll take this and then flip it over to zeros and ones. I just want to kind of mention that. So a lot of times we'll work with these Boolean arrays. I want you to think about Boolean arrays, but we'll need to represent them as zeros and ones. And I'm going to use view here. Those who are more familiar with NumPy know immediately what's going on. If you're not so much and you're unsure, as type is the better operation. Let me just point out that if we do, we'll get exactly the same thing. It's just a matter of whether it makes a copy in memory. So we'll use view, but that's only because I know that that's safe. And if you're unsure, use as type, which will just copy it. Okay, once again, key thing here, false 0, true 1. I've talked a lot. Let me go ahead and look at what we've got. We said we're going to threshold these. We're going to look and see what they are. Let's see what that did. All right. So all we did, we took what we thresholded a minute ago, and we're going to plot it up. We're going to put the bathymetry on the top and the threshold on the bottom. And what we can see is yellow, that's the ones. The purple back there, we've used a Viridis color map. So one is yellow and zero is purple in this case. But either way, let's just see that, yeah, we've detected seamounts. That's not awful. Let's go ahead and kind of zoom in maybe on some of these. At first glance, this is honestly not bad. But if we look closer, maybe we should have detected some of those. Um, Maybe if we look over here, there's a few we didn't detect that we should have. And also, let's go ahead and look at the overall. Notice we detected this entire big block back over around the volcanic arc, and we just labeled that whole thing as a seamount. That's really not very reasonable. If we labeled these as seamounts, that'd be fine. Those are arc volcanoes. We've labeled the full thing. So we need to do better. That's one of the issues with a symbol threshold is it's just that. It's a single constant value, which is not always the best thing to work with. So, all right, before we go on and do that though, let's investigate this a little more and let me introduce a tool that we're going to use. So we're just going to have this and we're basically going to be able to toggle on and off the seamounts. So we're going to use this quite a bit. It's actually in this repository, but it's just some simple tools to just kind of let us more easily interact with this. And with that in mind, just go back and do some of the things we did before. If we look over here, we can see that indeed those toggle on and off as we'd expect. Okay, cool. All right, we're doing an okay job. What can we do better? And I think it's pretty intuitive to most people. The seamount is defined relative to the topography around it, not an absolute value, right? We don't really care if it's at some specific elevation. We care what it is relative to everything else around it. So to do that, we're going to use a filter. Now, the filter is just, it's a concept that shows up a lot. You may be familiar with the convolution. Convolution can be, you can implement, some filters are convolution, some filters aren't. But a filter just means a moving window operation. These show up all the time in all kinds of things in numerical processing and in geology in general. Um, one of the things in this case that we might want to do is a filter that looks at kind of the background elevation. We might take a window and we might look at what's the minimum in that, what's the median. And one of the simpler things to do is take the window and look at the mean. That's a very simple filter. The simplest possible type of this is a uniform filter. Uniform in this case really means we're weighting everything equally. And in this specific case, it also means it would be square. We could use a non-square one, but we'll keep it square to be very simple. So it's just take a square region, and at each pixel, it's a square region around that, and at the center of it, it's the mean of all the values. So that's all the uniform filter is. It's very fast, very simple, and in this case, it'll give us the average topography in an area, which is kind of what we want for this background. So let's go ahead and take a look at that. Now, one thing I want to do here, so this we've used a window size of 50 right here, and if we drop it down, what we're going to see is it'll get crisper. That's no filtering at all. If we move it way up, take a bit to respond because the bigger the window it is, the longer it takes. But you see, we start to blur things. Now we smooth it out, and there's the full great big size. So the bigger filter you use, the larger effect you're going to have in terms of, in the case of a uniform filter anyway, of averaging things together. Just means we're using a bigger region, we get a bigger average. It's basically blurring it. So we might not want something quite that big. Maybe we want something around 100 pixels. Now, one thing to point out here. Sorry, I'm tripping over my own tongue. Value here is in pixels. We will work with real world units later, but for this part, this is just pixels. We don't care what the units are. It's all relative to the size of the image. All right. So one thing I want to point out too is you may imagine a moving window. What happens to the boundaries? So if we've got a 100 pixel wide window and we're over at this corner, how's that going to be handled? Now you could imagine one thing, we just don't process that data. We start 100 pixels in, but that would give us an array of a different shape. And really for most of these operations, we want to get back out the same size image as what we fed in. It's usually very handy and often very important. So it's important to know the boundary conditions are applied. We're going to use scipy.ndimage a lot. That's where we started with this, with the uniform filter in scipy.ndimage. And all of the filter functions in scipy.ndimage use the same boundary conditions. And I just want to pull up the help really quick here for it, just to point this out. What you'll notice is mode. Mode is basically the boundary conditions. The default is reflect, which makes sense. Basically, you imagine taking our values up here and whoops, and we basically put a mirror on this edge, mirror on that edge, and pad it out with kind of reflected values. Um, must also imagine constant, nearest, mirror, and reflect are very similar and subtly different. I don't want to get into the differences here, but you can see where this is going. You have a few different ways of handling it. These are all common boundary conditions. This is about all I'm going to say about boundary conditions today, but I do want you to remember it is important, and you should look at the documentation for whatever function you're using, just because quite often you want boundary conditions that are different. You may not want these, reflect is great in the case where we want to get this out, but if you're doing some other processing, you really might want it to be 0. There are usually options for these. Okay, enough about boundary conditions. Let's go on to our original problem. We've got this blurred image that makes a pretty decent background elevation. So next thing to do is to look at seamounts that rise up a certain amount above that background. So we're going to do the same thing. We're going to blur it with actually quite a large filter. That's big enough to give us, it's very similar to this. Here we go, put it all the way up. Very similar to, well, exactly like this. And it's a good way of getting kind of this, again, just background. We don't really care about any single feature, only the largest ones. And then we're going to say anything that's more than 500 meters higher than that. So pretty simple, pretty straightforward. And let's go ahead and kind of explore these. So I'm going to jump over maybe, this area. I'm going to make sure I get everything on there. All right, so here's our previous threshold. This is the just above 3,500 meters. And let's look at our new threshold. We didn't classify all of this as seamount. We're at least getting just local bumps in that. We did get these subducting seamounts. So before we were missing things like this, but now we're able to say, oh no, those are actually local highs. If we look over here at some of these smaller seamounts over, let's say maybe in this region. Oops, why is my, oh, that's because I hit it again. Sorry about that, folks. Let's jump that region. And we can see that before we didn't get them, now we're starting to pick those up. So we're doing a much better job. This is not bad. It may not be perfect, but this is pretty reasonable. All right, so the other downside to it, though, what about those guys? Do we really want a seamount classifier that classifies a 10 pixel wide seamount, or like these? If we look at some of these other seamounts, what we can see is that the regions are generally pretty inconsistent here. And it'd be nice if we got a nice smooth boundary. We don't want these little recesses. We don't want that hole in the middle or that hole in the middle. We really want something that's nice and clean. And this is a pretty common problem. You find a way to segment something, but the boundary is rougher than you want it to be. So one of the ways you can do that is to run a filter on the actual Boolean array. So the segmented result, the yellow part we got out here, we can actually filter that. We don't have to just filter kind of smooth, continually varying numbers. We can run some of these filters on things that are Boolean. So before we do that, though, let's talk for a second about, well, let's do this in 2 steps. There's the cleanup, the filtering, and there's also kind of morphology. When we have a Boolean array, something that's cleanly segmented and true false, we can take and do a lot of common operations. You might imagine buffering. So we've just expanded out, or eroding. So that's actually a dilation and erosion is the common term in image processing. But we can also identify holes within that. And these are all called mathematical morphology terms. So it's a general term for methods that apply to these Boolean arrays. And just kind of, apply common sort of things like that. Buffering, segmentation, where we separate out, this one is separate from that one, or we fill holes is one of those. I want to mention that partly because, one, it's a good term to know. We're going to use that a lot. And there's a link to the Wikipedia page here. But 2, it actually comes from geology. So this is actually the result of geologists, I think originally with thin section images, but I could be misremembering that. It's one of these things that's a very core foundational part to image processing, and very, very much comes out of geology. So just a bit of a tidbit there. All right, so let's talk about the fill holes operator. I won't go into exactly how this works. If you're curious about mathematical morphology stuff, the idea is we have a kernel similar to a filter, and we run that through the image, and we essentially can use its properties, kind of what its sum, if you will, to do certain operations. So it's actually really nifty how it works. And I would encourage you to look through them and try to understand it eventually, but it's kind of beside the point. All we want to know is, hey, can we fill in holes? So we don't want to have holes in our seamounts, and let's take a look and see whether or not that worked. We're going to zoom in where we had holes before, which was in this area. And one of the things we can see here, if you can keep the whole figure on the page, let's look at our original, and now we're going to fill holes. And bam, hey, we filled holes. All right, so it's literally one line, just single line of code, and we were able to fill in all these tiny little holes that would have been a pain to find manually. There's a lot more of them than you might realize when you start looking around, because there's a ton of these places where it's like 1 pixel hole, or 1 pixel hole there. And so filling them in is very useful. It's a very efficient and very fast operation. So just want to kind of point that out. It's really handy to have in your back pocket. It'll work in 3 dimensions or 4 dimensions as well. It's not just 2-dimensional. Okay, so I talked about smoothing up the boundaries. Let's go ahead and do that now. The idea we're going to do is run a filter on the actual classified segmented image. Interestingly, you might think of, I mentioned taking the moving window and trying to get background elevations. You might have thought of a median as being a common operation to get kind of a background. It's really common for despiking. Like if you have a bunch of spikes in your data, a bunch of noise, taking a median within a moving window is a really good way to remove some of those spikes without affecting the data too much. You can apply the same idea to a Boolean array. In that case, a median filter does a good job of being kind of it's equivalent to a majority filter if you just have 2 things. So what we're doing is we're saying, okay, a moving window, if all of the pixels, or more than half the pixels within that moving window, are one value, be it 0 or 1, then the center pixel will be whatever the majority of them are. That's what a median winds up being with 2 classes, right? You can expand that. If we had like 4 or 5 classes, it becomes a majority filter, which is also a pretty common operator. But the end result is that it smooths out some of these boundaries. It will fill in some holes, but not all. It will sometimes introduce holes. So one thing to note, though, the filters that we did before were the uniform filter, the fill holes. That was all lightning fast. I'm going to go ahead and hit run on this because it's going to take a second. A median filter has to essentially sort all the data in each moving window. You can actually get away without sorting it all, but it's still a much slower operation. It's not something that's can be expressed as a convolution. So I'm not going to show it a ton just because it is really, honestly, pretty slow. It's very useful. It's a really wonderful thing. And we are running 4 of them here just so we can see the different results. So it's not just that one of them is this slow, but it's not a simple operation, even though we use it so much. So you may notice when you start running a median filter on something, it's much slower than a lot of the other common filters. And it's just because it can't be expressed in a simple way. All right, so there we go. I was about to say it shouldn't be taking too long. Now, one of the things I've done, instead of using a slider here, what I want to do is I want to show our original, and we're going to look at how this cleans up. I like going to this area over here, really for no other reason than I think subduction zones are cool. Those of you who don't know me, which is pretty much everyone, I actually originally worked in subduction zone stuff for a long time, marine geophysicist by background, kind of a structural geologist, marine geophysicist. Anyway, so this is our original. A 3x3 window, you notice, slightly cleans it up. A 5x5 is going to do a little bit more. 11x11, we start to really do it, and then we can do 21x21, and we'll get them really smoothed out. But you can get a sense of what this is doing. And it's a very common thing to want to clean these regions up. And the right thing is very dependent on the data. So, it's good to experiment. I didn't do a slider just because it's just slow to compute. So it's easier to pre-compute a few and compare them. Okay. In the end, we're going to choose something in between. 11x11 looks pretty good. 21x21 is a little too smooth. I decided on 13x13. So I'm going to show this here. And we're going to run it. It'll take a bit. But this is going to clean things up. Now notice I ran the median filter. I also went ahead and filled holes. That's because the median filter can actually introduce holes. Let me see if I can find a place where it did that. Oh, right, the kernel's busy, so it's going to take a while. If you look around enough, you will find places where the median filter actually introduced holes instead of just filling them. I thought there was one in this area, but maybe there's not. It's not an uncommon thing to happen, and you often will want to fill holes after doing the median filter if you're using this to clean up. So sometimes you'll fill holes, run a median filter, then fill holes again. Okay, we've got a cleaned up single Boolean array, but we want to get a count of Seamounts, right? we have no way of knowing just from this data. It's all that's true, that's false, that's true, that's also true. There's no way of telling how many of these we have. So the next step in this is to go through and actually label these features. So this is another mathematical morphology operation. This is telling each distinct contiguous blob is distinct from another. Um, so the label operation in SciPy.ND-image will basically assign a unique value to each contiguous blob. And we can do things like define the exact connectivity. In other words, do we count just pixels that are, immediately on the side, or do we count adjacent pixels, or we can even count pixels that are 2 or 3 things away. But for default, we're just going to say they have to exactly touch, and we're going to leave it at that. Pretty simple, straightforward thing. We'll get an array that has a bunch of numerical values, one for each seamount. We'll also get a count of total seamounts. And 485 different seamounts. All right, that seems overall pretty reasonable. The color map I chose doesn't have that many unique values, so you know some duplicate values, but if you were to hover over, downside of making the screen smaller, or the text bigger, but the screen small, 223, and that one is 220. So notice they do have different values, even though they're the same color. Yeah, so now we identify seamounts. That was our goal, right? So we can do a little bit more with it, though. Let's say we wanted to look at the area of these. Usually we don't want to just identify them and count them. We usually want to do some sort of analysis. In this case, we might be looking at the area distribution to understand something about volcanic processes that are forming these, or any number of different things you might imagine. We might be calculating volume of each seamount. So let's apply some operations. So SciPy.ND-image has some ways to apply operations efficiently to a labeled region. Now, this is exactly the same as a for loop. It's a little more efficient, but I'm just going to show the function to do it. So we're going to pass in our basically this will count pixels. So in this case, we're not worried yet about area. We just want to do pixel counts. We're going to pass in our Boolean array, the labels for it, and then exactly which things we want to do. So this is, each one has a unique number, but it just goes from 1 up. So it's never 0. It always starts at 0 as the background, but 1 up to number of features. So 0 to 486 or whatever it was. Well, whatever it was plus 1. So that's why the A range plus 1 is there. All right, we'll look at that. That'll give us a count for each unique region. So it'll take, say, this region and count the total number of pixels within that. And then we'll just plot a histogram. Okay, hey, that's not unreasonable. We see a lot of small ones, and they start to kind of smoothly drop off. But area in pixels is really kind of useless for us, right? I don't really care about number of pixels. I care about actual area in meaningful units. So what we'll do next is we'll actually turn these into something we can actually talk about. So this is, again, a geotiff. We know where it is spatially, and we can actually get its cell size. Now, most geotiffs, almost all, are north-south pixels, and they're often square. In general, the reason you won't see like a cell size in this part, I'm calling it that, is because in general, geotiff supports things that are rotated, so rotated cells. And I'm just not going to bother with handling that case. So I'm just going to say this is the cell size of its north-south cells is in their square. It's just going to be A in this 6-element affine transform. But we can get that from our Rasterio, the actual geotiff that we're loading in here. However, if we think about this, this is in WGS84. That means that the area of a cell varies depending on where we are on the map. Now, in a lot of rasters, we wouldn't have to worry about that. If we're in UTM, you can forget that. It's all going to be relatively consistent. Technically, it actually does vary east-west in UTM, but it's just not worth calculating. So in this case, we're in a case where the area distorts significantly across the map. So let's actually handle that. Let's go ahead. We'll get our grid of pixels, and we'll calculate the XY positions using Rasterio. So it's against geotiff. We can just say like, hey, given this row and column, what's the latitude and longitude? So pretty straightforward to do. And then we can use what we know about how latitude affects area. So in this case, 1 degree latitude is constant, but the x direction shrinks as we move north. So this is the approximate distance of 1 degree of latitude at the equator, or 1 degree of longitude at the equator. And we're correcting for the decrease in the size of longitude as we move north or south. And it varies by the cosine of the latitude. Now, one quick note that sorry, I'm getting completely tongue-tied here. You may notice I'm squaring the cell size, but only multiplying a constant by by this. That's because y is not changing. So we have the y at the distance and latitude is constant, and it's only x that's changing. Okay, so we've talked a lot about this. Let's go ahead and get our actual meaningful histogram. And now this is starting to take a while to run. Mostly have a bunch of figures open, but we're almost to the end of this exercise. So now we've got something that's pretty interesting. We actually have square kilometers. We see this smoothly drop off, and I'm going to be a little geeky here for a second. Um, Note the shape of the histogram. This is, we have this long tail over here. We've got something out near 10,000 square kilometers. That's actually really common in geologic processes. So this is a log normal, approximately log normal histogram. And the way you get that, so it doesn't necessarily reflect anything about the process specifically, but the easiest way to get a log normal distribution is to multiply multiple normal distributions. So if we have, say, a normal distribution of width and a normal distribution of height, then we multiply the two together, the distribution of area will start to approximate log normal. If we do that a lot of times, then we'll get an exactly log normal distribution. So for geologic processes, we tend to have things that are kind of area or volume based. And basically, it winds up being, this sort of log normal pops out of the fact that it involves masses and volumes. So there is a lag. I just noticed a question that I can't answer, and I apologize I haven't been answering all the questions. I'm going to come back to them in the break here very soon. But I noticed the question about projection. I think I said this earlier briefly, but just to emphasize, the fact that we had to do this correction only is because it's in WGS84 geographic. If it were in a normal projection, we could just use the cell size directly, and we really wouldn't have to worry about this. But WGS84 is a really common projection, so I kind of wanted to show this as an example of how to do it. It's something that pops up a lot. All right, so I'm going to show one more thing, and then we're going to kind of review and take a bit of a break, partly because this is the end of the first part, and partly because I'm getting hoarse. So the next thing you want to do is usually actually do something with the data. You want to get a shapefile or a geotiff. I'm not going to cover that in detail, but I'd be remiss if I didn't show the example. So we can take and vectorize those regions. We have all these individual regions, scroll back up, and we might want to get a shapefile that has the outline of each one of these. So we might go through and turn each one of those features into a polygon and then save it as a shapefile. And that's what this does. So we're going to repeat what we just did. We're going to kind of go through, run that same analysis, get our labels, get our count, save out the new labeled raster, and then be able to go through and we'll say no data just to make it easy, but we can handle no data in geotiffs, write that out, and then start to have some fun. We can actually go through and write it out as vectors because we can use rasterio to vectorize the results and then save it. Notice there's a lot of code here. This is fairly verbose because I'm starting completely from scratch. We're specifying all the fields in the shapefile. We're doing quite a bit here. And while it's verbose, if you've ever used the sea-level wrappers, this is much less verbose than it was even in Python, even a few years ago. I've actually spent a long time working with GDAL and OGR directly, and this is a nicer interface to them. So I do highly recommend Fiona and Rasterio if you're working with this stuff. So this is meant to be kind of an example of how you might do that. Okay. I've talked a lot. I'm going to spend some time to answer questions here in a bit, but let me go ahead and review what we went over. We loaded the bathymetry in, so we looked a little bit at how to use Rasterio, but we talked a lot about just how it was stored as an array. We did some thresholding that didn't work very well. We did some better thresholding using a filtered version. So we talked about filters, how to do that, and then how to use that result. We got new detections. We cleaned up those detections. And then we separated those different detections into unique areas, calculated the area, and got an idea of what's going on. And if you wanted to look through a full example that did all this, you can load that up from the examples directory. All right, so we don't really have time for interactive exercises. So I consider this a take-home challenge if you're playing around with this on your own later. If you want to do this, sit down and think about two possible questions, depending on how comfortable you are with things. One of these is pretty straightforward. The seamounts often reach the surface. They form islands. We usually don't think of those as seamounts. So can you exclude everything that reaches the surface? And there's some built-in functions you might find useful. There's also, you can just do it straight with NumPy indexing. There's a lot of ways to do it. But if you look at that question and go, I know immediately how to do that, you might try something a bit harder. So mathematical morphology is a really useful toolkit, and if you're up for it, I would really recommend trying to do some tricks with these classified regions. So, for example, the thing I put it forward here is how would we join together seamounts that are within, say, 10 pixels of each other? If it's that close, it probably was the same seamount that we just inadvertently, disconnected. Um, and there are a lot of ways to do that. You could do it in ways that don't change the shape really much at all. You could do it in ways that potentially do change the shape. I will say the most efficient computational way to do it actually will change the shape a bit. So that is an option. But that's an interesting way to learn more about mathematical morphology operations and also potentially some other things like distance transforms, depending on how you do it. So there are some examples for these in examples folder. I think I committed those. And if I didn't, I will after all this. But yeah, play around with that later on if we have time. For the moment, I'm going to go ahead and take a break. I'm getting kind of hoarse. So yeah, I'll try to answer some questions in the Slack channel, and we'll be back here in about 5 minutes. So I'm going to sign out for a bit, and thank y'all a bunch. All right, and we're back, folks. All right, so we're gonna go ahead and move to another notebook. So this is the notebook kind of number 2 here. Um, and we'll kind of go on with what we've been doing. We're gonna use some of the same data, but we're gonna use it in different ways. So we're going to talk about slope gradients and things along those lines in a lot of detail because they're useful for a lot of different operations. So we're going to spend some time here doing this, but I'm going to do it in specific ways. We're going to talk about slope. We're going to talk about it in the context of making a hill shaded plot. So when you display this, in most cases, you often want to make a nicely hill shaded plot for display purposes. How does that actually work? How do we do it? And I kind of talk through that. And then we'll do some other exercises like find the toe of slope, which involves using second derivatives. So this is kind of these examples may not be the most exciting in some ways, but they're really good for learning these things. And it is actually pretty analogous to a lot of what you might do. And also, we're going to keep on using the bathymetry data just because it's kind of perfect for this sort of showing off basic things. All right, so let's go ahead and look at this in a little more detail. What we're going to do here, we're going to load back in the data we were working with before, exactly the same data. I did get a question about CRS, and it's a very good question. So let me just, one thing to point out is Rasterio stores its own CRS object. And so if we were to look at what that gives, we'll get, in this case, the string representation is EPSG, but if you actually look at it, it's a type, but you can do things like toString, toProj. So anyway, for those of you who aren't familiar, CRS is projection. So I'm just pointing out that if I hadn't mentioned that was in WGS84 and we need to know about it, Rasterio gives us ways to do that. So you have ways to get the projection and manipulate it in different ways. So I just want to point that out. Rasterio is more than just getting the data in. It will also at least let you know what projection it is and do some work on reprojection. It's not really a reprojection library, but it has a little bit of that there. Okay, back to the main topic. Let's go ahead and talk about gradients. So our simplest way to do this is to use numpy.gradient. And that's actually nice for a lot of reasons. It handles calculating gradients in a mathematical sense very well. What it'll do is it uses a, forgetting the actual name of the method it uses, but the idea is instead of just doing, x0 minus x1, it does basically x minus 1 minus x plus 1, and so you get a little bit wider central difference. There we go. So it's using central differences, except at the edges where it uses a different algorithm. But we'll talk about image processing kernels, but they all come back to being gradients, and NumPy gives a true gradient operation that's actually a good estimate. So let's look at that. All right, we've got the x and y components. Gradient always gives, this is the gradient of our z, in this case, our bathymetry, in partial derivative in the x direction, partial derivative in the y direction. Sorry, y and x, I said it wrong. But what you can see is that indeed our y gradient here is positive. We're coming from this direction going. So in this case, it's actually in pixel space. So our y is increasing downward and our x is increasing to the right. But anyway, we're going up slope and then back down slope. You see positive values, then 0 values where it's flat, and then negative values. And in this case, we're going from our right to left here, a little more simple. And we're going up slope, positive values, flat across top near 0, and then negative values we go back down. Nice and simple, and pretty easy to kind of see how that relates to topography. One of the things to point out, though, is it's pretty noisy. This is an operator that, in general, enhances noise. So if we look at a lot of regions, it can be hard to interpret. And we'll talk about that in more detail kind of as we go on. All right, so we've got rate of change in each direction. Next obvious thing to try is slope. So let's go ahead and calculate something very similar to slope. I'm not going to calculate slope just yet. I'm going to start out with gradient magnitude. So ideally before here, we would have put in our actual dx and dy into numpy.gradient. And it can actually take an array of, in this case, it would be an array of dx and a constant dy, but it can do that if it needs to. I didn't bother here because we're going to do other things that are going to work in units of pixels, but numpy.gradient can include your cell size and actually get accurate units for the gradients here, which is very handy. So we're going to do gradient magnitude, which we didn't correct for cell size, so it's just going to be a fairly simple value. It's not exactly slope, but it's very close to it. Let's take a look here. Okay, so two things. One, I've displayed the bathymetry data the same way you're used to seeing it. I've displayed the gradient magnitude in a way that may be a little unusual to some folks. So white is actually values near zero and black is high values. The reason for that is it makes a nice visual product and it stands out. Looks a lot like a hillshade map. So it's a common way of showing some of these image gradients for smooth surfaces like bathymetry, because it's easier for the eye to interpret. So that's what's going on here. And notice again, it's actually, there's a lot going on here, but really gorgeous. It's nice multi-beam sonar. You can see, faults. These are probably actually normal faults, so definitely normal faults in the subducting oceanic crust before you hit the toe of the accretionary prism there, or the erosional frontal prism in this case, not really accretionary. But anyway, I'm geeking out. Subducting seamounts are really, really cool. But you see all this detail that's not obvious in the original. And that's one of the nice things about a gradient. It enhances noise, but also enhances detail. So let's use this to look at actual slope. Gradient magnitude is great, but notice these values. What the heck does 200 mean? It's hard to put that into immediate terms. So a slope in degrees is a little nicer to work with. So we're just going to do this. And same idea, we've just displayed. You notice they are very similar in terms of overall kind of appearance here. We've got these same outlines of high values around the edge of the seamounts. I'm using a different color bar, so they look quite different, but I've set the maximum to 30 degrees just because the maximum is significantly higher, but most of that's noise. 30 degrees is a pretty realistic maximum slope, even for these super steep things. It locally can get over it. They're going to be small areas. It really lets us see some of the details, but it's the same information as what we saw in the gradient magnitude. Gradient magnitudes here, slope, we've changed the units, but we haven't really changed the information. Let me go over how we did the slope calculation because I breezed by that. The cell size, we're going to keep it constant. I know it changes. I'm just going to brush that under the rug for the moment, and we're going to pretend this is a nice projection where we can do this with simple cell sizes. So I put a single cell size in meters because our units for the z direction are in meters. And basically, we're going to take that's distance of 1 degree latitude in kilometers, multiply by 1,000, get to meters, multiply by our cell size in degrees, which we got from Rasterio up here. We're going to put that into the gradient so it knows how big a steps we're taking. And then we'll have our dx and dy, except they'll be properly scaled. When they're properly scaled, we can calculate slope very easily. We're going to have the arctangent, inverse tangent, and that's basically pretty straightforward to do. So it's arctangent of the hypotenuse of the total. So essentially, we know how far we went. It's rise over run, but because we got separate dx and dy components, that's why the hypotenuse there. And the hypotenuse, if you remember, that's how we got the gradient magnitude calculation. So this is the gradient magnitude, and slope is just the arctangent of the gradient magnitude when everything's properly scaled for units. Okay, I've talked a whole heck of a lot. Let me go on to something more interesting. So let's talk about what we've looked at so far versus hillshade. This really nice looking gradient magnitude map is actually not what you use during hill shading at all. It's often a nice thing to have, but it's not a hillshade map, and hillshade shows a different level of features. Gradient magnitude, really, you emphasize these large changes that are pretty obvious from the raw data. So I'm going to scroll back up to the bathymetry plot. And what you can see here is, yeah, I mean, we could have guessed that was a steep edge just from the raw data. It does highlight these smaller features pretty nicely, but it really emphasizes the steep edges. Hillshade, on the other hand, is going to emphasize smaller features. So let me explain what hillshade is. A lot of you have probably used it, you know what it is intuitively, but we take the local angle of the surface and we take some sun angle and we basically say, okay, is that illuminated? If so, how much? And if they're perpendicular, that's highest illumination. If they're in shadow, that's lowest. That essentially is all it is. So a lot of this, you'll notice, is very similar to the slope calculation we just did. In fact, you'll see slope right here. We also do an aspect to take care of the orientation. And then that's some trig, but basically it's the dot product. You can put all this in terms of dot products. It just happens to actually be faster and more memory efficient trig. Didn't used to be the case, but processors are different these days. It's the dot product of we have the local topography that has a normal vector. And then we have some illumination vector that might be coming in like this. So it's the dot product of the normal to the surface with the illumination vector. And the closer they are to parallel, because again, it's the normal to the surface, so it's perpendicular. The closer those two are to parallel, the higher value you get. All right, let's look at that. I've said a lot and haven't done anything. Oh, why is it not? Give it just a second here. Are we struggling with number of figures open? So one note, in this tutorial, I will come out to maxing the memory out on my laptop. That has to do with me having an old personal laptop, but that may be what's going on. Oh, we're good. I'm sorry. Okay, so this is a toggle plot. So I did this before. We're just going to toggle these layers on and off, and we're going to compare gradient magnitude, hill shade, and the original. So let's zoom in maybe somewhere in here. And let's look at the gradient magnitude. That's what we looked at before. All right, we see those steep slopes. Really looks nice. We can see a lot. Let's look at the hill shade. It's just a hill shade plot. And you may look at this and go, oh man, that's garbage. And I have actually tried to scale it so that it's reasonable. But the reason you're looking at this and saying, oh, that doesn't look good, is because this alone lets you kind of see stuff about the long wavelength structure, whereas hill shade alone only gives you information about the fine detailed structure. The reason that hill shade is so nice is when you combine it with something that gives you information about the long wavelength structure, like say the original bathymetry, you get a plot that shows you both. And if you were to combine gradient magnitude and the original bathymetry, which I didn't do in this tutorial, but I should probably add an example that shows it, you won't get anywhere as near much information as this combining this rather noisy looking hill shade plot with the original bathymetry. Let's talk about how to do that in Python. It shows up a lot. I think people forget about it. Matplotlib actually has a built-in function to do it. It's quite nice. In some ways, I always wanted to add a ax.im shade. I actually rewrote a lot of this stuff in Matplotlib ages ago for this particular part. I was meant to add a function to do it more easily, but at the moment you'll set up in two ways. You call light source, and then you basically are going to combine your data and color map it. So it's going to be an RGB with kind of the hill shaded version. We're going to blend that in different ways. This is overlay. Well, it's different types of blending. And those, if you do image processing, you'll hear about them a lot, but you may see overlay and like dodge and all that. We're not going to use dodge, but the two things that are relevant here are overlay and soft. And they're ways of combining the grayscale or any scale, any RGB image with another RGB image, but it works very well. You can make transparency. You could make the hill shade layer transparent and put it on top. That's a valid way, but the overlay and soft blending are a little better visually. So let's go ahead and look at that. Once again, I've talked a lot about it, but I'm not showing it. Oh, one thing to note here, I did downsample this a bit. That's all that is. It's just because this uses up a lot of memory at peak memory usage, and I didn't want to encumber things too much. This is a little lower resolution than the actual data, but it still looks, really nice. And you will see it's a little blockier than what we're looking at before. I did downsample it here, but we can do the full res version if you just have more than 3 gigs of memory on your laptop. Yeah, anyway, you see both the large scale features from the bathymetry, the color changes, and then you see the fine scale features very nicely from the hill shade. And this is the big advantage of hill shade over just over gradient magnitude. Okay, so let's step back to gradient magnitude because it is a type of edge filter. So what it did is it detected big changes in our data, right? So those are edges. And edges are often features that we want to detect in data, be it an edge of a grain and thin section, or a lineament and aerial photograph. Those are all types of edges. So edge filters are very useful, and they show up in a lot of different ways. Most of them are related to gradients in some way and gradient magnitude. So I just want to kind of mention that and talk about these in that order for that reason, and we'll see exactly how. So we did numpy.gradient, it's a true gradient. There's also something called a Sobel filter. A Sobel filter is the thing that you'll hear immediately in edge detection for images. it's almost exactly a gradient. So the only difference is it does a little more averaging, and the units are wonky because they don't account for the total value of the filter. So it's a factor of 8 difference. So I'm going to compare the two, but notice this correction factor of 8 to get the units the same. That has to do with the actual kernel it uses, and I'll show you that here in a second. But let's look at Sobel versus a raw gradient. We're going to make a fancy figure here because, hey, fancy figures are good. Let's just zoom in on some random. I seem to like showing subductions on, so we're going to zoom in here. Zooming, come on. All right. You may look at them and go, yeah, they're the same. And they really almost are. I've corrected for units with a factor of 8, and they are almost completely identical. If I didn't do that factor of 8, you'd see big differences in magnitude, but the overall information is the same. If you look really closely, though, I mean, really, really closely, what you'll notice is the Sobel filter does smooth just a tiny, tiny touch more. You can see it pretty well up here. That's the gradient, and that's the Sobel filter. So they're almost the same, but they're not 100% identical. And let me just mention why that is. I haven't talked about kernels a ton, but a filter, the moving window that we apply, it's a kernel that we're applying weights to. So a kernel is the simple types of filters that can all be done quickly. Use a simple kernel that we can apply to that moving neighborhood, and the kernel is just a set of weights that kind of gets applied and then gets summed, and then we move on to the next window and do the same thing. Either way, the gradient kernel would look kind of like that, and a Sobel filter is actually averaging a little more above and below. So this is in the X direction. We just have a single thing for gradient. We're just averaging stuff nearby a little bit. They're almost identical, as you can see. Reason for the factor of 8, if you sum up the absolute value of this whole thing, you'll get 8. All right. The reason I'm spending so much time on this, it's really common in geology to want to do both things that might use a Sobel filter and things that use numpy gradient, and it's important to point out the differences. Use gradient, an actual gradient function, when you need to do something with units. And if you don't care about units and you just want a fast operator and has some nicer properties in some ways and avoid some aliasing, then the Sobel filters is a better choice. So it's a matter of whether you care about units. Okay, so I'm spending a heck of a lot of time talking about this, but let me talk about one more, and that's a Gaussian gradient. So with a gradient, you could imagine taking just a straight, difference, on either side. So that might be just, one minus the other. Imagine that's a ruler, a very stiff, small ruler that we're putting on the edge of the slope and measuring that at each point. Imagine instead of this stiff, small ruler, we used a big, long, flexible ruler, kind of something that's very, wobbly. And go back to grade school and think of whenever you had a ruler that was kind of flexible. I'm missing something here that would be a good analogy, but a rubber ruler that will bend easily. So we might press it down against the slope to measure slope. And it might have a rough piece over here that would bend up, but it would kind of force things over this way. And that might have another thing over here that's a bit rough and force things up. But it'd be really caring more about the center and a little bit about the edges, but mostly in the center. But it's averaging over this larger area. That's what a Gaussian gradient is. So another way to visualize it is we could filter the image with a Gaussian, which we'll talk about in a second. And then take the gradient. It's the same thing, but you can actually do if you're worried about the Gaussian gradient, you can skip a step and just calculate the gradients directly. Yes, a French curve. There we go. I thought a French curve was this. Anyway, it doesn't matter. The whole point here is that we can do this in a way that is a little more smooth and doesn't care about these sharp changes. And Gaussian filters are incredibly common because they'll let you smooth in a way that's very visually nice. And Gaussian gradient filters are very nice because they let you get noise information about gradient without amplifying noise. All right, so I've some one step, but I want to show the X and Y components. All right, heck of a lot of talking here, but it's good to see this. So let me zoom in on some of these regions we're looking at before so we can compare them. There we go, flat spline. It's actually, the term spline comes from splines. That's right. They were the things that people used to use exactly like that. Yeah, that's it, a flat spline. And we're definitely reticulating splines. All right, so I just want to point out the the differences here. Notice how noisy the Gaussian, the raw gradient is, and notice how we're still getting the same large scale information out of the Gaussian gradient, but we've nicely smoothed over this fine scale detail. And that's an adjustable thing. It's not a fixed amount. So let's talk for a second about that adjustable part. Sigma is what it's called. That's just what it's called in the math. It's the standard deviation of a bell curve in normal distribution. It's actually exactly the same formula. So it's in pixels, but they don't necessarily have to be one. We could do 0.1 sigma and it would still be, you know, it'd be a tight sort of thing. But the more you increase it, the larger it gets. It's not going to be a 5 sigma. It's going to be probably like a 20 pixel wide filter because it's going to do weights that go smoothly out. But it's still, the bigger it is, the more smoothing you get. And let's just kind of play around with that a bit. All right. So we've got this, and this is our gradient magnitude. Zoom in on an interesting area here. Excuse me. And we're going to just dial it up and see what happens. And notice we get smoother. We dial it up even more. It's going to take a little while to compute, but we get pretty smooth. We might look at some other area here. Come on, there we go. Let's maybe look at some of these. Oh, yep, I need to remember how to use this. All right, so let's dial that back there. I'll let 0. Come on, you should not take long to calculate 0. Oh, it's calculating everything in between. So what happens when I move the slider fast? But we're just going to notice these little blips of noise. Those are actually probably individual ship sounding that they're using in this. So, you know, we just might blur it out a little. And you'll do a nice job of removing some of those once it updates. There we go. All right, so it gives you some idea. And if we bump it further up, it'll do even more smoothing, and we can even smooth out some of these, you know, very real features. But sometimes we want to do that. I just want to give you a chance to play with it, get a sense for kind of what you're doing when you play with this, because we will use Gaussian sigmas quite often throughout the rest of this. They'll pop up in a lot of cases, and we're still waiting on it to update this. So I'm a little concerned that my computer may lock up here, but we seem to still be having Zoom and large Python notebooks cohabitating. Hey, there we go. Yeah, so we can eventually blur everything out. That is probably less useful. All right, so we've done a lot of this, and it's great for finding these larger scale changes and suppressing noise. It still gives us an edge filter that isn't a noisy edge filter. So this is kind of where we wanted to get to with the calculating hill shade. We got to that a bit ago. You know, this essentially, not this, excuse me, this image way back here was what we said we're going to get to, and I talked about some other stuff. So let's go on to the next actual exercise we said we wanted to do. That's going to be toe of slope. So sigma here, again, is this, you know, amount, but we're going to use, instead of just a first derivative, we talked about Gaussian first derivatives. Let's look at second derivatives. Toe of slope is a curvature problem, right? So if we're talking about something rising up and then it starts to rise up out of the plane, we want to find that point of curvature where things change. So it's not just the change in the first derivative, it's where the inflection point here for the second derivative. So we'll see a peak in the second derivative over this point, and that's what we're looking for. And then actually a negative if it goes back and turns down this way. So we have a negative in the second derivative at this point. So we're looking for maximums in the second derivative. Now, second derivatives are even noisier than first derivatives. We're taking the gradient of the gradient. We're really amplifying noise. And that's why you'll often see Gaussians used there. So that's actually a Laplace operator. So second derivative of a Gaussian, we're going to apply this Laplace operator, which is, again, just second order Gaussian filter, and then look at the magnitude. So let's go ahead and run this real quick. Now I've got a toggler again, and we're going to zoom in on a Seamount here. And let's look at this. Okay, so toggle it on, off. One note about the colors. The reds are positive and the blues are negative. And actually you can't see that because it's a little off the screen. There we go. Those are negative values. Whoops, there we go, negative, and the reds are positive values. So toggle back and forth a bit here. And what you'll see is the positives are generally at the kind of toe slope we're trying to recognize. So we're trying to kind of find that point, right? This point where it rises up out of the plane and maybe bends around there and then does this. We're trying to find that line right there. So in this case, it's maybe not the peak exactly, but it's, a high point in this Laplacian, and that is pretty close there. All right, with that in mind, we might take and do some filtering on the Laplacian. So let's go ahead and do what we did before. And we're going to take the positive values, but then we don't want to get these positive values. So notice something here. We also have positive values where we're inside the seamount. So we want to avoid those. We want to have like this outline, but if we've already classified the whole thing as a seamount, let's not find these secondary slopes inside that. So with that in mind, what we'll do is we'll rerun our seamount detection. And then we'll go through and basically use that to mask out areas that we don't want. But our main thing is still going to be a threshold on this Laplacian up here. So I'm going to filter for positive values. Positive, we get everything's red, but I want a little bit more than just not negative. I want to be up in, some threshold. Now I'm not going to play with it in this specific case, but we can play with it a bit and change this threshold. So what we've got is we're taking significantly positive Laplacian plus not in a seamount we calculated earlier, and then this is what we get. We've masked them out. That's this part. We just said masked equal. That's so we hide everything, and then just give me the yellow things where it's true. And let's zoom in on this real quick. And that's not too unreasonable. Like we're finding that. Now there's one problem here. This is a pretty broad region, right? We want to get this exact nice little narrow line. So how do we take this broad region that we've segmented out and turn it into a nice clear line that we could use for toe of slope? So that's another mathematical morphology operation. So that's going to be a skeletonization. You also sometimes hear it called a medial transform. And the idea behind that is that we're going to take and just basically get the center of this thing as we go through. And actually, yeah, it's a good question. Why don't we just use the zero contour? So I could have mentioned that, and I probably should have more, but let me show it visually here. So if we were to use the zero contour, there's two reasons we're not. One is that the zero contour is it's obvious here, right? We can trace, so this is an excellent question, by the way. We can trace the zero contour through here. But if we go out here, we're gonna have zero contours all over the place. If you look closely, that's negative and that's positive. That's negative and that's positive. We're flipping back and forth between negative and positive all over the place through here. The second thing is the zero contour is actually not quite what we want. And if we look more closely at what we're detecting, the zero contour is in the middle of the slope. So it's actually right about here, and we actually want to be over here. So that's the two reasons. One is that it's very noisy, and the two is actually it's not where we want. We want the peak and not the zero contour. As far as the other question about it being a Laplacian of Gaussians, yeah, that's actually what this is. So to give some, sorry, I'm going to switch back over because I can't remember what we were just discussing. Yes, it is the same as the Laplacian of Gaussian. That is purely a naming convention. I'm not even sure if it's European versus US. I think it is actually more the image processing libraries I'm working with versus versus other common notations. But yeah, Laplacian of Gaussian, Gaussian Laplace, same thing in this case. But yeah, we want the maximum and not the zero contour is the other question. All right, so I'm rambling a whole heck of a lot. We're back to here. We want to thin this down and get an exact edge, right? All right, so the zero contour would be kind of above here. We actually want to be in the middle of that peak. So let's do that. Let's take and skeletonize this region. Skeletonize, we'll just kind of take the medial, it's the medial transform, but really it's not exactly the center. It's the center of mass over a window. So it's a little weird in some cases. You'll get tails. If you use a circle, you'll get kind of little three prongs coming out, but it is still a very useful operation for these things. And let's zoom in and take a look at the way it works. And what we've got before, we had kind of these sort of things, broad region. I don't think I zoomed in on the same seamount, did I? I did. Good. Okay. Um, so before we had this broad region, and now when you look at it through here, you see that we actually did a pretty good job of finding that toe of slope that we wanted to find. Um, so, overall, not bad. And we've got a nice thin region for it. Okay, so the take-home challenge is going to be less fun this time because I'm running out of time to really make the tutorial. So we didn't do a great job with toe of slope here. There are a lot of knobs you can turn here to do a better job. And so my take-home challenge to you is, can you beat this? One of the things that this doesn't try to do well is connect up. Like, for example, we just end here. We'd really like this to follow around. We probably don't want to detect things like that or these little blips out here. So there's a lot you could do to do this cleaner, and just play around with it, come up with a few ideas, see if you can clean it up. Maybe, trim off things like that. Think about ways to do those things. That's a very open question, but also one where you could start with just playing around with some of the thresholds I gave here. What if you change that to, like, 5? You get the idea here. And if you did that, you'll notice that, well, we don't do a very good job of getting it, but still that threshold is an open question. So I'd encourage folks just to kind of play around with it, see what you can do, because there's a lot of things we could do better. Okay, I forgot to explicitly say it, so I'm going to modify the note. Well, I'm not going to because I lost my toolbar, but break time. So we'll there we go. Now it says break. Back in about 5 minutes. We're going to go over one more notebook. I will warn you, the next notebook is both the coolest examples, it's all the fun stuff, and the stuff that I didn't have enough time to really break it down in detail. So it's going to be a little more freeform with going through it. We'll have nice big standalone examples, but I'll have, unfortunately, a little fewer sliders and widgets and talking through it. But we're about to do the fun stuff. So please hang around. This last notebook will be the most interesting examples and the places where we'll start to just use some kind of complex and a little more crazy operators that thankfully these libraries make it very easy to use. All right, so back in 5, and I'll see all y'all soon. All right. So, welcome back, folks. Hopefully, I had a chance to step away for just a little bit. Um, we're going to go ahead and move on to the final notebook. So, this will take the next at least half hour or so, but I do want to be a little bit of time for questions. I hope it'll round out most of the time. We probably will end a little bit before the scheduled time on this. But regardless, we're about to dive into some of the really fun stuff and do kind of more complex operations. Not say what we were doing before wasn't fun, but we're going to do more than maybe the first you might immediately guess with image processing. And some things are very easy these days that weren't in the very recent past. So a lot of image processing techniques have come a long ways, but not only that, a lot of things that were research grade image processing have become extremely commonplace and easily implemented. So let's start out by going on to lineament analysis. Now, this is a pretty common thing to pop up, and there are a lot of different things that people mean by this. What I'm going to do in this case is worry about small lineaments, so obvious fractures in rock that are visible in aerial photography. Sometimes people mean things like a large scale ridges and more topographic features. I do want to mention that this same idea is often applied to that. It's a very closely related thing, and there's some topographic fabric metrics that were independently invented back in the 80s that actually do this same thing. So you can actually apply this to other data than just images too. Um, so yeah, at one point, as Matt just pointed out, apparently the latency is quite high. So I think questions are going to be a little laggy, but we'll kind of come back to those hopefully here in a bit, and I will circle back in the chat too. All right, let's go ahead and get started. We're going to dive in and try to identify some lineaments in some aerial photography. And just to point out, this is from National Aerial Image, NAIP, which is National Aerial Imagery Program, which is USDA, really great stuff. It's all free. You can find it, search for NAIP and USDA, and you'll be able to get this. It's usually 1 meter RGB imagery for most of the United States. So definitely really good stuff. All right, back to it. We're reading it in, and I do want to mention one thing here when we come to RGB imagery. Rasterio has a band on first axis convention. So in other words, the first, if we were to index, let me actually just make a new cell here. I forget the keyboard shortcut. Well, anyway, let's do this again. I'm gonna what the heck? Let's just do this. And let's print it before and then after. And I want to point this out because it's a really common thing to need to do, and there's some easy functions to remember for it. All right, so by default, when we read it in from Rasterio, we're going to have a shape that's going to be number of bands and then height and then width. And most other things, including Matplotlib, scikit-image, lots of other various libraries have the opposite convention where we have height and then width and then number of bands. So there's a very easy NumPy function to do that. This was added not too long ago, so if you have a really old version of NumPy, you might not have it. When I say not too long ago, I think I might mean 10 years ago at this point. So anyway, it's just a handy function to know about. You can do the same with swap axes and roll and transpose and a few other things, but this one's nice because it works the same in both ways. To translate, you move axis, the data, the first axis and the last axis, and it'll swap. The same call works in both directions, which is very nice. So if you need to write it back out, you can call the same thing and it'll swap it back around. All right, so I'll point that out because it's something people hit a lot. This is our data. Now, this is near Arches National Park, near Moab, Utah. It's not in either. It's just an area I picked that had clear lineaments, but they weren't necessarily incredibly obvious. So I deliberately picked one that was a little less obvious than some. And, these things we're looking here, these are joint sets that have been preferentially weathered, maybe some small faults there too. But we're looking at joints in sandstone that have been weathered and have vegetation growing along them. One of the common things you want to do when you're working with this is to measure the orientation of those. And when we do that, we normally would go through and kind of digitize these manually. and it takes a while, and there's nothing wrong with it, and you definitely get better, nicer, cleaner features. But there's something to be said for throwing an automated solution at something like this, because you sometimes will get some features you might otherwise miss. Like, are those actually other joint sets up here? Yeah, they probably are. They're a bit of a different orientation if you look. They're like this, but the other ones are like this. So there's some subtle features the automated stuff may pick out that you might miss by eye. It's also just time consuming to digitize things. But even when the hand stuff is always cleaner and better, but there's a lot to be said for being able to do this quickly. So let's see if we can detect those and say something about their orientation. Now, one thing to point out here, uh, for this, we don't really care about color. It's all kind of the same color anyway. And a lot of these methods are easiest on grayscale imagery. We will work with color in a bit, but for right now, we're going to go ahead and just get an average, simplest possible grayscale conversion. So we're going to average over the bands here, and then get something that's just a grayscale version. There's other ways to do grayscale, but that's a good enough for our purposes one. All right, we've got a single band of imagery now. Before we had three-dimensional array. This is RGB three-dimensional array. Now, if we look at this, well, I won't bother printing it out. It's just two-dimensional. We can go back to what we're doing before. We've worked a lot with gradients and edges, and all those are edge detectors. So let's go ahead and use the Sobel filter that we talked about before. Now, Sobel in SciPy.ND image is a little convoluted because you have to jump through generic gradient magnitude. Socket image has a single function call that'll give you the gradient magnitude from a Sobel filter, which is usually what people mean when they say Sobel filter. So we're just going to use that here. Also, the first time we'll start to use things out of Socket image instead of just SciPy.ND image. So let's go ahead and see what that looks like. All right. Hey, not so bad. One thing to point out here, I don't have it on yet. Never mind. Let's go ahead and zoom in on a region here. I'm going to use this region. We'll come back to it a lot. This has some clear features. And let's look at the Sobel filter. Okay. Now, yeah, it's picking up edges, but these are really noisy. We're picking up all kinds of things, every little tree and shadow, and we're getting like, look at how strong that edge right there is from that little. I don't even know what that is. Maybe a rock sticking up, maybe not. But we're really detecting a lot of things we're not interested in. It's a very noisy filter. So another thing we can do, we talked about Gaussian gradient magnitude. That's a great way of getting gradients without being too noisy. Notice the sigma parameter. So I'm just choosing 3 here, but you can play around with that, and I would encourage you to if you'd like to work with it. So let's zoom back in on that area again, and let's look at the Sobel filter. All right, again, picking up lots of these edges, but too many. And the Gaussian filter, Gaussian gradient magnitude, notice we're really, the largest features really are the edges we're interested in. We're still picking up some of the other things, but we're really getting some nice high values in the regions that we're interested in. So that's one of the nice things about the Gaussian gradient magnitude. It's significantly less sensitive to local perturbations. All right, so let's imagine we took that and let's threshold it. So again, remember with this, I know it looks like hillshade. I'm just keeping the same display convention I did before. The dark values are the highest in the way I'm displaying it. So if we were to threshold it, we would basically be looking for all the regions that are dark through here. And arbitrary threshold, we'll play around with it down here, but we're gonna get a slider. Start out with something in the middle. So we're looking for high regions of gradient magnitude based on the Gaussian gradient magnitude. We're not playing around with the width of the sigma. We're fixing that for the moment, but we're just going to look at different thresholding values. And you can play around with this, start to progressively drop things down. That's maybe too much, maybe something in between. And then if we look at this, maybe we look over, some of these other things. Basically, we can start to see some of these are picking out fairly nicely, others not so much. But regardless, for all of them, we're getting fairly broad features. And remember before we talked about our skeletonization feature, filter. So the toe slope exercise we did earlier, this looks really similar to that. You might go, okay, well, let's skeletonize that. We'd probably, get a nice line along these, and then we could look at maybe trying to filter out some of the others. That's the fundamental idea behind a canny filter. So the canny filter is, let's take a gradient, let's essentially threshold it and skeletonize it, except that let's be intelligent about that threshold. The idea is to not use a constant threshold, but use a threshold that if we've been above it, we can drop down and then pick back up. And then we'll take and skeletonize everything. So it's a combination of thresholding and skeletonizing, but doing so in a little more intelligent way that tries to preserve continuous edges. So it's a really interesting idea, and thankfully it's a single function call. And let's go ahead and look and see what we get. This is a canny filter again, just to repeat that. And what we see is we have indeed gotten these nice continuous linear edges around the features that we're interested in. And if we look in general, let me just zoom in on maybe a pretty big area. Oh, sorry, I have to actually I keep on clicking it, even though I've already clicked it. But the orientation of these really does largely match the lineaments we're interested in. Now, there's a lot of this that doesn't. There's a lot out here, these little bits, these curves around all the trees. But if we were to look at the orientation of the straight parts of this, on average, it would line up pretty well. Okay, so that's a canny filter. Nice, simple, thin line along the edge for an image. Really useful thing, pops up a lot. How do we get the straight segments of this, though? We've got all these nice thin edges. We need to go through and identify which portions of them are straight and get something that we can use more directly. So you may have heard of a Ho transform, or I've heard it pronounced 20 different ways. I'm going to say Ho transform. Feel free to correct my pronunciation or use a different one. The key thing here is that it detects straight lines. So you give it an image, and it's a simple idea of rotating the image progressively, and then summing along that to get, basically, if you've rotated at the angle of the line and you sum along it, well, it's going to give you a high value. And then where it gives you that high value gives a sense of the offset, and then the angle you've rotated gives you a sense of the slope. So it gives you a y equals ax plus b type equation. The key thing there is it doesn't give you endpoints. You look for local maximums that correspond to an infinite line. And it's very useful, and it's a great way of detecting straight linear features. Once you've got something that's kind of an edge filter, for example, like this, where we've kind of found all the edges. But it doesn't help us to get infinite lines. What we want are more line segments. We don't want, oh yeah, there's probably an infinite line through here at this slope. We want to go, no, there's a line in this location, and there's a line in that location. There's another type of Ho transform that tries to do the same thing, but probabilistically fit specific line segments from that. That's a probabilistic Ho transform. It's thankfully, again, a single function call. There's a fair amount going on here. It's not a simple thing, but it's simple for us to use. So let's go ahead and try that. Let's take our canny filter up here, where we've determined the edges and limits, and then let's try to get individual straight line segments. Now, this has a lot of parameters. The biggest one is the length of the lines. What it does is it looks for lines of a specific length that have less than some distance of gaps in them. And obviously, the longer your line is, probably the longer tolerance of gaps you want. So I'm going to express this to give us a single slider as a ratio, but the two parameters that you can play with independently are the length of the lines and the amount of gaps you allow within that line, if that makes sense. So it's saying, like, okay, if we've got this thing that could be a line, but it has a gap of 5 pixels, that's fine. If it has a gap of 10 pixels, that's not fine. That's essentially what the line gap part is. So we're going to play with this with a single slider that's just going to be length of the lines, and let the gap be a constant ratio of the length of the lines. All right, so let's play around with this. We're looking for specific lengths of lines. So in this case, we are at 10 pixels. And if we look for longer lines, we'll get these longer things, fewer of them in this case. Although some of that's the gap part. If we look for much longer lines, we'll get, give it a second, there we go. We'll get fewer longer lines. You can tune this a lot, but it's actually surprisingly pretty good and useful. It's a good filter to know about. And there's a tuning factor, but we're finding straight lines of edges. That's what we want. The big downside, though, is often it's not going to detect the exact edge we want. It's going to be much more like, well, yeah, that's the orientation, but I really want to detect this one. So we'll come back to that in a second. Let's go ahead and do something with this. So we've gotten those lines. I'm going to use some more specific settings, I'm going to use a line length of 30 pixels and allow up to 5 pixels in between to not be a high gradient or not have a thresholded value at them. And then let's go ahead and look at their orientations. Let's make a rose diagram. That's why we want to do this. All right, so this is really not bad. This is, I tuned things a bit to get this number of line segments detected, but we're seeing orientations that really do match our actual fracture directions. The big downside is that we're still not detecting some of the features, visually that seem to be the most clear. We're also detecting an awful lot of things in this orientation. Sun is coming from, I actually don't know if you can see my mouse, but sun is coming from the northwest to the southeast. And so we're picking up a lot of things that are perpendicular to the illumination direction. They're all over through here. That's not ideal. Ideally, we'd like to be independent of the way it's illuminated. We're also picking up, for some reason, a lot of straight east-west things. I actually am not sure what those are. But we can see kind of at least this clear orientation is the fracture pattern. We can do better. This is neat. This is very low effort for what it was, but this is very much something we can improve on. So one of the ways we can improve on this is to pull out a tool that's very common and called a lot of different things. So this is the structure tensor. The structure tensor shows up all the time in geology. We just call it other things. It is, it's basically a measure of the consistency of orientations, specifically of gradients in images. So we use the same math and the same idea to do things like shape indices and deformations. If you make Flynn plots, it's actually kind of the same idea. Coherence in seismic is actually directly, basically a structure tensor derived attribute. Now there are things that say, hey, I am a structure tensor derived thing, but the math underlying coherence is very similar in all ways. We use this sometimes in geomorphology. There's a series of quantitative basically they're meant to be topographic fabric indicators. So are we in something that's highly eroded or not? But they are literally a structure tensor of the local slope gradients. And it was invented before the image processing folks did it, but it's how this works. So we call them 1,000 different things in geology. In image processing, it's called a structure tensor. This is what it is. You take a moving window, you calculate, well, first off, you calculate the gradient in the same way we did before. So we have an X and a Y component of the gradient at each pixel in our image. We then take a moving window around, for each pixel, we're going to take all the dx and dy gradient components within some window around it. And we're going to build up a covariance matrix of those X and Y vectors, so the X and Y components of those vectors. That covariance matrix tells us not only how strong the gradient is on average, what's the magnitude, but it tells us how consistent it is. If they all sum in the same direction, then we've got a consistent, strong gradient everywhere throughout there, and it tells us the direction of that gradient as well as how consistent it is and how large it is. That's really great for things like lineaments. So the same idea shows up in all kinds of ways, but again, it's covariance matrix of vectors in a moving window. That's all it really is, and then we'll take the eigenvectors and eigenvalues of that covariance matrix. Now, if all that sounds like a heck of a lot of math, it's not as bad as it sounds. We're just saying, if everything's going the same direction, that's what we care about. We don't care if things are really moving in large directions, they're all going in different ways. It's what's this total sum of all these vectors, essentially. So let's go ahead and do that. This is an involved example. This is one that I intended to split up, but kind of ran out of time. So I'm going to talk through this a little bit, and then we'll look at it. What we're going to do, structure tensor is thankfully just one call in scikit-image. And there's a convenient function to calculate the eigenvalues. Now I mentioned we take the eigenvectors and eigenvalues of this 2x2 covariance matrix. Actually doing that is much slower than using some simple, you can actually do eigenvectors and eigenvalues of a 2x2 matrix if it's symmetric by hand. So this is literally, if you look at that function, it's some simple algebra. And we'll kind of reuse some of this. But notice that we get 3 elements out of the structure tensor call. That's actually the structure tensor, but because it's symmetric, there's only 3 unique elements. And that'll be one for every single pixel in the image. We will have this, actually 4 values, three unique values, but technically 4 values for every pixel in the image. And that has some different things going on. Sigma is there is actually that's sigma in the gradient, the Gaussian gradient magnitude. So rather than using a moving window, they do actually use moving window. But anyway, it's there's a few different ways to tune this. The biggest knob in this case is actually sigma, which is very directly related back to that Gaussian gradient magnitude. Normally, in other cases, you can tune the size of the window as well, which is very useful. You typically want to use a very large window, which this particular function would not let you tune. But if you write the equivalent from scratch, you could use a very large window to look at things like ridges. So like if you have actual topography data and you want to identify ridges, you might use some massive window and just not do it at every pixel. Because what you want to do is we have this detailed topographic surface, but we want to detect the overall ridge. So we need a big, large amount of data. All right, I'm saying a whole heck of a lot here, but not doing a whole lot. 2x2 matrix. We then are going to take the eigenvalues. Again, that winds up being just some algebra. And then we can turn that into the eigenvector of the largest eigenvalue. So even though we just get the eigenvalues out, basically, because this is all 2x2, you can do this with simple algebra. We actually can get the largest eigenvector as well. So that's what we're doing here. The math is extremely simple. It actually does have a flip for the fact that the image starts at the top and goes down, and so there's a flip y inherent in all this. That's baked into this math. But anyway, we can get dx and dy components of this is again the eigenvector of the covariance matrix. So this is not the gradient x and y. This is essentially how consistent all of those gradients are across the entire, like this moving local neighborhood. So the magnitude of that is going to be a very good indicator of how consistent things are. And the direction actually tells us, essentially which direction the gradients are going. So it actually is a lineament itself. So what we can do, we can take the magnitude of that and we can just look for things that are above some percentile. I'll make it 90%. I won't display every one because it gets messy. So I'm going to spend a lot of time on plotting, but this is just going like, yeah, let's only display every 10th one in each direction. And this really works well. Because each one is not just a magnitude, but it's a vector, we're not just going to show, hey, we selected these pixels. We're going to show, hey, we selected arrows in each of these pixels. And it really will show these lineaments nicely. And it's a common technique that gets used a lot. So let me show this. What we've selected stuff that's large magnitude. And then we've got a direction in each one of those. And you can see we're actually, picking out the edges pretty well. We can play around with that. Let's zoom back out. It's also pretty interesting sometimes to play around with the threshold. So let's make this maybe 70%. We're going to get a whole lot more arrows. And notice again, we have a lot more arrows, but they're still concentrated along these edges. Now, one of the downsides, the more we drop that threshold, the more we start to see, again, the influence of shadows. So let me show some of those in here. Basically, we're finding, like these are all shadows. Those probably are too. So, you can see where this is going. So the more you kind of decrease that, the less reliable things are. So that's why it was set all the way up at 90. We might do 95. Again, this is just the magnitude of these. So we're only looking for the biggest changes. And we can see that those mostly correspond to the features we're interested in. There are a few that are shadow related. There are a few that are, that's a shadow, that's a shadow, that's a shadow, a few other things. But notice if we change that, we have changed the shape of this distribution a bit. We haven't changed the main things about it. One of the things I want to point out, this analysis was pretty quick. We got these major lineaments. Notice we do see this second orientation, and that's this orientation that's a little different up in that corner and over here. So we're kind of seeing two subparallel sets here that you should be skeptical about. These you should never take this analysis as something that's this is what it is. But if you go in and look, you'll see that we do have kind of this orientation that's more this way in some parts, and then you have an orientation that's more this way in other parts, and we see that nicely, and it's actually pretty hard to pick out by eye. So yeah, that's a structure tensor. There's a lot of other use cases for it. You can do things like look at local anisotropy. You can use it to do various kind of superpixel sort of things. Well, I say superpixel. You can use it to essentially make filters that move through and smooth, basically structurally oriented filters use the structure tensor is really what it boils down to. So we call them structurally oriented filters in geophysics and in geology, but it's the same idea gets applied to image processing sometimes. I won't show that, but that's the idea of kind of this technique. So like I said, these last couple are getting a little more like, hey, here's a big fully worked example, but hopefully you can kind of see how it works and play around with it. And I'd really encourage experimenting with some of this on your own data. There's a lot more to structure tensors than just these arrows I've shown here. There's a lot you can derive from them. They're very, very nifty and fairly easy to do. All right, so I'm gonna take a drink of water really quick. What we've been working on so far has all been this very large scale data. You know, we've been looking at half the Western Pacific. We've been looking at, the aerial photograph isn't that big, but still it's an area a kilometer across. Let's really switch gears. One of the things I originally hoped to emphasize in this tutorial was that we're talking about methods that apply to any scale. Image processing is nice partly because it is very scale independent, and not that you don't have to think about scale, just that a lot of the methods don't care and give you knobs that you can adjust the way you need. So with that in mind, let's jump straight to a thin section. Thin sections are images, a lot we can do with this. We're gonna stick with the orientation theme. So in this case, we're gonna try to get a shape preferred orientation. So try to look at the fabric in the rock and just get, there's a lot more we could do with this. I'm gonna keep it very simple and we're just gonna try to make a similar rose diagram to what we did before, except that we're gonna do it by trying to detect individual grains and then look at the alignment of those individual grains. So what's their orientation? Can we get image moments is actually where it comes from. So let's start out. This is from the British Geological Survey's collection. I just grabbed an interesting looking thin section. So first off, let's talk a little bit about what a thin section is. We've taken a piece of rock, we've glued it to a piece of glass, and we've polished it down until it's very thin, around 30 microns. That means it's transparent. So, ooh, that's a really good question. And I'm interrupting things. I'm going to come back to that one. Anyway, we've polished it. It's transparent, and we're shining light through it. Now, those of you who haven't worked much with optical petrology, we're going to work with cross polars here, and I'm sure you've probably heard the term, but I will say a little bit about what it is. I am not a petrologist, so I'm going to sound a little stupid with some of this. We just stuck in the cross polars. What that means is basically we're looking at optical things caused by the anisotropy of the speed of light through the actual crystal itself. So this is birefringence is the reason for the colors we're seeing here. So it's the same soap film bubble effect, but it happens with mineral grains. And it is actually a property of the mineral. So the color doesn't tell you anything directly, but the more strongly anisotropic it is, you can actually get out to certain colors that you wouldn't get through otherwise. So in this case, it's an amphibolite. So it's something that's going to cause fairly bright colors to occur. If we're looking at more feldspars and quartz, we wouldn't get some of these nice pretty colors as much. I chose this for two reasons. One, the nice pretty colors let us do some things with color that's kind of interesting. And two, if you look, there is a significant preferred fabric. There's a fabric in this rock. It's an amphibolite. It actually does actually have a bit of fairly strong shape preferred orientation, and we can quantify that. So we're going to work with the not the plain light data, but with the cross polarized data. And I'm going to toggle back and forth a little bit. If you look closely, you'll notice these aren't aligned. One of the other things I wanted to do in this section was show how to take and automatically align the two images, which is a very interesting topic that's not too hard to do. But it's going to be beyond what we'll do here. So we're just going to work with the cross-polarized version. Now, let's also take and segmenting these background parts off is another interesting exercise. But in the interest of time, let's go ahead and just ignore that. So what we're going to do is work with just the center part. That's going to be this, just arbitrary indexing. So we're looking with a smaller piece. This is really to make visualization easier because it's a little hard to visualize some of the stuff we're going to see on the full image. Now, one thing I want to mention here, we're going to try to take these grains and we're going to try to identify each grain based on color, right? So we want this to be a grain. We want that to be a grain. And if we look closely, there's quite a bit of variability in color within the grains. They're not just one homogeneous color. So we want to be able to group common colors that are spatially close to each other, but also not just do an exact color match. And even an exact color match is tricky for reasons I won't get into. Color distance is important, what space you use, but we do want to be able to smooth this out. We want to group things spatially that are similar in color without being too different. Now, this in general is a pretty common task in image processing to want to segment things based on color. There's a ton of things that do this. So it's actually an area of somewhat active research, or was very recently. It still is. It's kind of shifted more towards machine learning approaches, but it's very common, and there's a lot of different methods. And so, like scikit-image, for example, has like 20 of these, and so does OpenCV and other things. That there's a lot. A lot of times they're called superpixels. Again, the idea is you're grouping regions of similar color together. So that's like it's one pixel essentially, but you're wanting to make it a larger area. That's where the term superpixel comes from. Some things are analogous to a watershed. So you'll take a gradient and using the color information, and then essentially say, okay, where does this change? That's the edge of the watershed, kind of watershed approaches. Most are clustering methods. And then really you can train a CNN to do this quite nicely if you have enough examples of similar things. But we're going to use a pretty common one that's become quite well known, and it's called SLIC. It's simple linear iterative clustering, and it uses k-means. So if folks aren't familiar with k-means, the idea is that you're trying to pick out, given there are 5 groups, find the centroids of each of those groups in dimensional space. So usually imagine clusters of points. It's finding, okay, we got this cluster of points and that cluster of points. Here's the center of that one. There's the center of that one, without doing anything beyond saying, I want 2 clusters. So it's unsupervised. The neat thing about this is it's actually doing it in 5-dimensional space. So it uses the X and Y coordinates directly in the clustering. So that gives you some spatial consistency, as well as the RGB values for color. And that's essentially the idea. It's take X and Y and RGB, make that a 5-dimensional vector, cluster that 5-dimensional vector using k-means with this many things. There's some additional quirks. It has to do with the transform and other stuff. We'll play around with some of those quirks, actually. All right, so let's go ahead and start working with this. So one note, we're going to be getting out of this grains array is going to be a similar labeled array to what we did before. So with the Seamounts, it's going to have 1, 2, 3, 4, 5, 6, 7. Each grain that it identifies is going to be a different value. But there's a lot of grains in this, and so it's really hard to show these in a color map. This is different versions of. Sorry, folks. Different versions of things. Anyway, I'll get into that here in a second. They've recently introduced a parameter that wasn't there before, and I have different versions in different parts of this. Anyway, we're going to get a labeled kind of 1, 2, 3, 4, 5, 6 image out of this from it, but we're going to display it in a different way. So rather than trying to display everything, I'm just going to show the boundaries. scikit-image has a nice way of doing that, where it just will overlay boundaries on an RGB image. But keep in mind that what the actual data we're getting out is, instead of these yellow boundaries that we're seeing, it's going to be essentially a constant value all inside here, and then another constant value all inside there, and another constant value all inside there. So it's a labeled array, some other things. Okay, so let's look at what it did. That's not awful. It's picking up some grains, it's grouping some stuff together. It definitely shouldn't, but it's not bad. We're on average getting a lot of the grains, and not only that, the boundaries it's choosing do at least correspond to grain boundaries. They're not just random. So it's often picking out grain boundaries, even if it's linking some things it shouldn't be, and dividing other things it shouldn't. Now, in general, doing this well is outside the scope of this, and it's something that there are a lot of approaches to, and really, it's a tough problem, and I'm not going to talk a whole lot about it. So you can dramatically improve on this, but this is pretty okay. Let's go ahead and look at some of the parameters, though. I gave a couple things here. One is sigma. Let's go ahead and just bump this up to like, let's bump it up to 10. Sigma is, again, Gaussian distributions. This is Gaussian gradients. I'm Gaussian gradients. It's actually smoothing it before it goes in. So it's just a straight up Gaussian filter. So this is going to smooth it a bit more. What we'll see is we'll have a little bit smoother boundaries. So I'm going to run this one and then we'll talk about it. The next thing we'll talk about is the number of segments and compactness. The number of segments and the compactness metrics are actually the two biggest knobs to tune in this one. So let me just kind of show this. Notice I smoothed the heck out of it. And while we're getting grain boundaries, zoom in here, they're often not where we want them to be. So that's one of the big downsides to applying too much smoothing. It shifts the boundaries significantly. So that's why it was tuned down to like 0.5 initially. We'll go ahead and leave it at 0.5. All right, so I'm going to run that again just to give you a sense of what it was. Number of segments should be roughly equivalent to the number of individual things you want to classify. So in this case, it's the number of mineral grains. Notice it's set to 1,500. That was just an eyeballing, like, how many do I think there are here? Well, 1,000 maybe. I don't know. Let's put in 1,000, see what it looks like. Maybe 2,000. So that's kind of the other big knob to turn. And as soon as this finishes, we're back to what we started with. So just give you an idea of what it looked like originally. Let's try dropping it down to 500. And each one of these takes a while to run. So what you'll see in the end is it's going to choose much fewer, and it's going to group things in ways that may not really make sense. So this is a pretty big knob to tune in these cases. And if it ever finishes. All right, so again, the boundaries themselves are reasonable, but look at what it lumped together. If we actually zoom in here, it's lumping all kinds of things that it really shouldn't be into one grain. So yeah, all these are one grain according to it. And that's the downside to making it too low. On the other hand, if we make it too high, let's go ahead and put in 5,000. And it's going to take a while to run. What we're going to get is a ton of every little difference in color picked out. We're going to have way too much. Really should have pre-computed these. So as you can see, it's a bit slow. This is doing k-means clustering in 5-dimensional space with 5,000 clusters. That's why it's as slow as it is. It's actually a much faster algorithm than pretty much anything else in this category, though. One of the nice things about Slick is that it's fast. So even though it seems slow here, it's better than a lot of the others. So again, now we're seeing lots of cases where it's breaking up grains that shouldn't be. One thing I want to point out with this, there's another technique that I'm not going to talk about called region adjacency graphs. So we use graph theory to look at, okay, we have this one and that one. They're side by side, but how different are they in terms of color? Well, if they're similar, group them and then keep on going. So you can apply some methods that take these over segmented images and then start combining regions by color, and it'll keep the boundaries, but then you will keep a boundary that existed at some point, but you may combine this grain with that grain and then combine it with that grain and that grain, or maybe not that grain. The idea is that you go back and apply a simplification operation, and that works quite well too. All right, one other thing I want to mention, we'll put it back to our original value of 1,500, and that's compactness. This is how square things are. If I really bump this up, let's just put it on so you often want to vary this by multiple orders of magnitude. It's a weight on the spatial coordinates. The higher you make compactness, the more you're going to get essentially squares. And the lower you make it, the more you're going to not care about spatial weighting. So compactness of 0 doesn't use spatial stuff at all. In fact, there's actually a more efficient way to do that. You can say ignore connected, and it will only do the clustering in 3 dimensions. But we often want to do it in, a slight weight, but not a lot. Let's go ahead and put it up to like 100. 100 may be too much. This may not even show what I want to. We'll get very square things, but we'll get square things that try to sort of follow colors. And like I said, this was the part I didn't have as much time to put together, so I'm spending more time doing it on the fly, and I hope it's not too much to sit through. All right, there we go. Yeah, this is basically squares, and we can do something in between, and you see it follow colors more. But if we zoom in on this, it did at least try to follow grain boundaries. It just basically made the clusters evenly spaced. And that's really what that thing does. You'll often want to vary it. 100 may be entirely reasonable for a lot of images. These are not absolute values. You often want to change it on like, a log scale. So you might start with 100, then 10. The default value is actually 10. Then try like, all the way down 1e to the -6. But don't change it by a small amount. Change it by a lot. It's a weight that needs to be changed significantly. Okay, let's dive into a more complete example on this. So I said before we cared about shape preferred orientation. Let me run this again with our original grain, just so I can talk a bit about what we're going to do. So one of the things we haven't talked about is ways of extracting information about the shape and size of our classified regions. So we did size with the seamounts with area, but we could have also collected things about their orientation and their kind of overall kind of long axis to short axis. These are image moments. You can imagine if we had a bunch of points, a point cloud, we can get the image moments by taking the covariance matrix of the point cloud and extracting the eigenvalues. That's what the image moments essentially correspond to, but image moments are a different technique because images are regularly spaced. If you were to take a point cloud, each pixel is a point, and do the same thing, it's incredibly slow and incredibly memory intensive. You can do this, you can get the same result because everything's regularly spaced with some simple math that I'm not going to go into, but it's one of those nice, beautiful things that falls out where suddenly we can do this as sums in different ways. So image moments can give you a covariance matrix of the distribution. The reason that's useful is, again, this is like long axis, short axis of a grain. And in this case, that's exactly what we want to look at orientation. Even though we haven't done a great job classifying these grains, we see that in general, we have a long axis and a short axis. We have a long axis and a short axis. And even though these are very irregular regions, you're getting just the overall kind of both ratio of long to short, so how angular they are, and then the orientation of that. We're going to leave the ratio out, but we're going to look at the orientation. Now, socketImage.regionProps actually has a lot of very useful things in it. And let me just add in something really quick. We'll go ahead and do it because we haven't run this yet. Pull up the docs on it. It does a lot more than just the image moments even. So it's a very useful thing to know about. Apparently I can't talk and type at the same time. All right, so I'm just pulling up the docs, and I want to point out what all we can get out of it. We can get things like area, centroid, convex area. There's a lot of these that come out. Eccentricity is another thing that you can actually get out of the image moments. So it's that's again this kind of like, is it short and stubby or long and narrow? You can get the orientation out, the entire tensor, the eigenvalues, all this stuff. It all comes out of image moments, and it will actually give you the exact image moments. And this is just, it's very, very handy if you have a bunch of classified regions. This is, again, meant to work on Boolean arrays. Well, not Boolean, it's the labeled arrays, but the idea is we have this is a class. It is essentially a Boolean array. We can get these moments out. And then this function works on labeled arrays. So instead of like a Boolean, hey, nothing, and then this, it's a series of like background 1, 2, 3, 4, 5, like these exact things. All right, so I'm talking a whole lot about it, but we're going to go ahead and calculate that, get out the inertia tensor, which is, again, in this case, it's the covariance matrix I mentioned before. Get the azimuth of it, and just make a quick rows diagram. So I've talked a whole lot for what in the end is going to be just a rows diagram of the approximate grain orientations, but all done automatically with just a little bit of tuning on trying to segment the grains. And once this finishes, well, this is where we get to stare at the screen. And I thank you for following me along so far. This is about to be the end of the tutorial, which is a bit early, but let's go ahead and look at this first. So let's go ahead and zoom in here. What we see is the rows diagram, and indeed we see orientations this way a lot, which is that axis of it. And then if we look over in other areas, we will see, that's not what I wanted to do. Sorry, folks. In other areas, we might see things that are a little more north-south oriented. So like through here, these are much more north-south, which is kind of that main axis. But we're mostly picking up on the actual fabric in the image. If you look at this without anything else, and you were to visually estimate the fabric, what you'd see is that, yeah, I think I draw it this way, but maybe I draw it straight north-south as well, depending on exactly which grains you're looking at. And we've mostly captured that. In this rose diagram. So we've done a decent job, even though we didn't do a great job with the grain classification. On the whole, we got an okay estimate of the shape preferred orientation. So not bad for just throwing a couple simple methods at it. Now, I just want to say, if you're actually doing this analysis, you'd spend a lot more time on getting that grain segmentation right. You'd probably apply a lot more sophisticated methods, and tools like ImageJ and a few other things are really great for this. I'm just trying to show you kind of some examples of this. It is in general something that you can spend a lot of time on, and people do, and is something I actually don't know a ton about. So what I gave you was here's a common method used for this general technique. Let's see if we can apply it to a thin section. I'm pretty sure we have some photographers on here that are getting very annoyed with me because I do not do thin section work. So anyway, that's actually it. I forgot to write up a take-home challenge for this final bit. What I want to say, though, is that this entire third notebook is really a take-home challenge. Can you essentially go through and tweak these things, make them work for you, and try other ideas like this? Both of these are, can you do it better than I did it before? I think definitely try if you're up for it. And if you really want to take home challenge, I'll try to write up the example later, but you can look into ransack and feature detection and actually try to line up your cross polarized and plain light images that don't quite align. Anyway, that's a whole different story. Hope y'all have enjoyed it. I've certainly been rambling towards the end and my voice is going out. So thank you for sticking around. I'll join the chat for questions. Any of you doing this later on, feel free to reach out. Software Underground Slack channel is a great way. You can contact me directly. My email is joe.kington@gmail. You can find it easily enough. I'm also easy to find my email from the GitHub link as well. So yeah, that's essentially it. Happy to hang around and answer questions in the chat. But I think we're a little laggy to do it live. So I'm going to go ahead and end things here. So thanks for following along. Cheers, folks.